Hi, this is another example of Poisson's ratio, and there's one concept we didn't cover previously about Poisson's ratio is this concept. This formula, basically you see elastic modulus E, you see G, which is shear modulus, you see V, it's Poisson's ratio. So in other words, there is a relationship among the three, and this formula basically says it all. If you are curious, I would suggest you to do that. Pause a moment to go to the inside of your back cover to, for example, choose a 36 stainless steel and find its G and then find its E. Then put into this formula, or you can actually, instead of finding G and E, how about we just find an E and Poisson's ratio V, then calculate using this formula. Calculate your G. See if this G is going to be the same as the value in your book. And so do that. It should be pretty much matched up. Okay, so assume you did that experiment to verify this equation works. Now let's go ahead, look at this problem. How this concept will help with this problem, because sometimes you might only know two of the three, then you can actually find the third one. So this is one problem for that. This is aluminum specimen. They didn't tell us particular aluminum, so you can then they told us this G, and they told us this G. Okay, and now let's see. So the diameter is given, D0 is given, and the gauge length L0 is given, and the force 165 is used to elongate the gauge length. So the gauge length basically is your delta, okay, your delta L. Elongate, because they said elongate the gauge length 1.2. Then determine modulus of elasticity. They gave us a few properties. The G, shear modulus, is given, and also sigma y, that is actually the yield normal stress. So when you remember the yield normal stress on that sigma epsilon curve, here's elastic until right here at the yield point, it's no longer elastic anymore, it becomes a plastic region, right? So that's when, here's Artemis. So this is going to be where it's no longer elastic anymore. So let's think about it. They give us the force 165, and we know the cross section is a circular. Can we find the first step? Can we find our normal stress, right? Stress is going to be force over area, and our force is 165 kilonewton, and the cross-section area is going to be pi r squared, or pi d squared over 4. So d is 25 and over 4, and this gives us a unit of millimeter square. Now let's think about it. We're talking about kilonewton over millimeter square would give us a unit of gigapascal, right? Okay, so the rest is just put the numbers into calculator. 165 divided by pi, then divided by 25 square, then we're going to times 4 after flip. Then I have an answer here is 0.3363 gigapascal. So that's going to be the normal stress, okay? And then they want us to find modulus of elasticity, which means is E. Then in order to do that, we need to find this normal strain, epsilon. Epsilon definition is going to be the change in length over original length. And it told us the elongation of the gauge length is 1.2 millimeter, and the entire length here is 25 millimeter. Oh, I'm sorry, that's going to be the diameter. So the entire length is, gauge length is L0 is 250 millimeter. Then put into our calculator 1.2 divided by 250, then we'll have an answer as 4.8 times 10 to negative 3. So that's our normal strain. And remember, strain has no unit. Okay, so the last thing we can calculate is going to be figure out the elastic modulus. That's our Hooke's law. During the elastic region, Hooke's law is going to be the slope of stress over strain. So sigma over epsilon. And the sigma is 0.3363 gigapascal from step 1. And epsilon is 4.8 times 10 to negative 3. By the way, one thing I want you to pay attention here, I ignored at the beginning. This stress, right, when this 165 kilonewton apply down, that's essentially it's 336.3 megapascal, correct? And this value is, well, less than yield stress. So which means this value is somewhere here, which is inside the elastic region, right? So which means Hooke's law exists at that time because it's still at elastic region. It's less than this yield stress. Therefore, we can use Hooke's law for this. And here we are. That's why we're doing it. Then you have 0.3363 gigapascal divided by 4.8. Then we'll have 0.07 times 10 to the power of 3. The unit will be gigapascal. Then that means it's going to be 70 gigapascal. That's our elastic modulus, or modulus of elasticity. All right. Then we figure out the E. The next thing is determine how much of those forces cause the diameter of the inspection specimen contract. So it's telling us how much for this circular shape, the cross section, what's the diameter? The diameter is going to change. And what's the change in that, right? So what's not the diameter, it's actually changing diameter. So how do we do that? That's going to be the lateral dimension. So whenever they ask you the lateral dimension, we're first thinking about its Poisson's ratio. So do we know Poisson's ratio here? We don't. However, we know a few other things. So we do know our G, because G is given. And guess what? You just calculate your elastic modulus in this step. Then you can find Poisson's ratio. Is that neat? So you have G is equal to E over 2 1 plus V. Our G value is 26 gigapascal. Our E value is 70 gigapascal over 2 and 1 plus V. And from here, we can calculate our Poisson's ratio. Let's take a look. And so I have 35 over 26, then minus 1, then we will get 0.346. And this has no unit, right? It's dimensionless. So knowing that, we can find how much contraction happened in that circular section, in the lateral section. How do we do so? Knowing this, do we know Poisson's ratio? It's negative epsilon lateral over epsilon longitudinal, right? So this is 0.346. And we want to figure out the lateral strain. And however, do we know the longitudinal strain? Yes, we do. It's this step 2. This is basically longitudinal direction. Longitudinal, okay. And that's 4.8 times 10 to negative 3. So knowing that, we can figure out the lateral, how much contraction happens. So 0.346 times 4.8, that gave us the value of 1.66 times 10 to the negative 3. And we do know we expect to be a negative value because it's contracted. So the last step, how much the change in that diameter, right? Because we know epsilon lateral is the change in the diameter over change in, I'm gonna use the big D, indicate the diameter. Change in diameter over the diameter original dimension. So this is negative 1.66 times 10 to negative 3 lateral strain, and change in the diameter. And what's our original diameter? Is that given? Which is this value, right? The 0.25 millimeter. So knowing that, we can figure out how much has shrunk in the lateral direction. So 1.66 times 25, I have about negative 41.52 times 10 to negative 3 millimeter. That's, this is a very small number. How about we change millimeter to micrometer? So that's negative 41.52 micrometer. That's the change in diameter. That's the last thing we need to solve, right? Changing diameter, how much the cause the diameter to contract. Okay. All right, so that's it. As for this problem, we basically giving E and G. You can find the Poisson's ratio, and for this problem, you actually find E first, and so that's the entire problem. That's pretty neat. Thinking about this actually happening in real life, you can put the specimen there and apply forces and measure how much has been elongated, and then you can find E, and if you know the G, then you can find Poisson's ratio. Then you can actually measure the contraction on the diameter size. Alright, that's all for this problem, and I'll see you in the next one. Bye now.